Thank you so much, Alvaro. I really appreciate the introduction. So like Alvaro said, I've been here for 10 years, attending CTNT since its inception in 2016. I think it was in August that year, and it's been in June ever since then. I've been really happy to be a part of CTNT all these years. I started off as a senior undergraduate, and now I'm in my last year as a postdoc, starting a tenure-track job in the fall. So it's quite a journey, starting at CTNT and ending up here again at CTNT. I want to say a little bit about CTNT before I start in my talk. So when I was talking to Alvaro last year at a workshop, I mentioned if CTNT was going to run, and he mentioned that the funding situation wasn't completely ironed out yet. And he had, I think, half-jokingly mentioned that we might be able to get funding for CTNT from like a sponsorship like Slim Jim or Ruffles or Lay's. And I don't know how serious that was. I know that it's running now and it's funded now. I don't know if Slim Jim's sponsoring it. No? Okay. That's a bit of a shame. But I think it's fantastic that it's still running because at least CTNT has given me an opportunity to sort of widen my mathematical community, and it happened at a very crucial step in my career, which was at the end of my undergrad when I was starting to think about more serious math research. So I think CTNT fills a sort of niche in this regard, where there's not many other conferences in number theory that are aimed at these starting students. It's nice to have, and I'm thinking of the Winter School, for example. The Arizona Winter School is a very big number theory thing happening every year, but those courses are more aimed until recently at advanced graduate students, whereas CTNT is aimed at these beginning students. And it's nice as a beginning student to know that your mathematical community is larger than you think. You meet all these other students in the same position as you, also learning about this sort of brand new mathematics and advanced number theory and uncommon topics. It's a really good feeling to feel like you're part of a community. So I'm really happy CTNT was created 10 years ago. I'm happy it's still running 10 years later, and I'm happy to be a part of it again. But I actually like to take this moment to thank all the current and previous CTNT organizers for all the hard work they've done in putting this together and keeping it alive. So let's all thank them now. Okay, so in that case, let's start the math talk. Maybe I can get an extra 3 minutes to my talk. Oh, it just evens out. Okay, perfect. Okay, no worries then. So this talk is going to be on, as the title says, elliptic curves, torsion points, and Galois representations. But specifically, I want to introduce you to these topics and then show you a project I had with an undergrad student at Ohio State on studying these things. It was from an elementary group theoretic point of view that I had him working on it. And I'd like to convince you by the end of the talk that you can also think about these cool topics in elliptic curves without having to know a wealth of arithmetic geometry. Okay. So in the interest of time, I actually want to skip the first couple of slides. I know that Alvaro in his mini course talked about the basics of elliptic curves, and I think that the people that are just starting to visit today and not the summer school probably know about elliptic curves. In this slide, I want to skip a couple of slides, but I want to bring to your attention the definition of elliptic curve. The intuition, at least, is that elliptic curves have a way to add points on the curve and then produce potentially new points on said curve. Okay? And so this can be pictured over the real plane with something called the coordinate tangent method, where it's a two-step line process. As you can imagine, if you're taking lines and intersecting them with elliptic curves, there's some sort of intersection measured by polynomials, and it ends up being a bunch of algebra. It works out because of the geometry, though. So with elliptic curves, you have a group law on the set of their points. And to be a little more specific, if you have an elliptic curve E defined over a field F, this is a group law on the set E of F rational points on your elliptic curve. These are points with coordinates that live inside the field F. Okay? And this group law works out, and it makes your set E of F an abelian group. Okay? And if it's not clear by now, I'm going to gear this talk towards the students in CTNT. If you're a more advanced person, I apologize. Maybe you'll get something out of the talk still. But I'll show you this research project in the second half. Okay. And this picture actually is from a book of Joe Silverman on the arithmetic of elliptic curves, who's in the audience, and actually will be giving a talk pretty soon. So stay tuned for his talk as well. Sort of the golden standard for learning elliptic curves as an introductory graduate student. Okay. And also, I'm just going to, well, it's a group, so I'm going to have an identity element. This is often called the point at infinity. and I'll call it O or 0 most of the time, okay? But the thing to take away here, if this is new to you, is that your point in infinity and this sort of projective coordinate system will have rational coordinates, okay? Okay, so I'm assuming this stuff was covered in Alvaro's mini-series, but if you want to see these slides and actually read through the previous stuff I just skipped, I have my slides on my website right now, which is just tylergenao.com. You can also read ahead if you want, or if I go through a slide too fast, you can look back at that slide. If you're watching the recording, this probably won't be on my front page, but it'll be on my website somewhere. And if it's not, you can just email me for a copy. Okay. Okay, but I want to really start with torsion points. So for the rest of this talk, I'm just going to assume my ground fields F are number fields, which means they are finite degree extensions of the rational numbers. And so if I'm looking at an elliptic curve over a number field, I can imagine its coefficients for its equation living in F, but also they live in the complex number C, so I can base change my elliptic curve from F to C and look at this group instead. In this group E of C, I'm going to call a point with finite group order a torsion point. Okay. So a torsion point is a point such that there exists a positive integer n for which n times p is 0, where n times p is this addition under this coordinate tangent method I mentioned earlier, excuse me. Okay, so torsion points are torsion elements from group theory. These are just finite order points. And if you want to be a little more specific, I'm going to say that if n times p is 0, I'm going to call this an n torsion point. All right. So if I collect all the n torsion points on my elliptic curve, this forms a subgroup of E of C, which I'm going to call the n torsion subgroup. And I'll often write this as E bracket n, or just say E of n. And there's general theory that shows that you have exactly n squared n torsion points. So n squared points on your elliptic curve of order dividing n. Okay. We'll actually talk about a more general version of this result, which we'll need for understanding Galois representations explicitly. But for now, I just want to note that you can attempt to count all the n torsion points you have. Okay. So torsion point definition is pretty algebraic. There's also some symmetry if you picture the torsion points on an elliptic curve. So for example, on this curve, I have a point on the bottom in blue, which I've called P. I claim that from this picture, you can show that this point has exact order 6 on your elliptic curve. So it's a 6 torsion point, a little less precisely. Okay. Okay, so I want to talk about division fields and Galois representations next. Do we have any questions so far for me? Okay, so if not, let's go back to this definition of a torsion point. I say my point P is n torsion if m times P is 0. There's something interesting that happens with torsion points. So it is often the case you're thinking of a point of the form, having the form x comma y, where the x is the x coordinate, y is the y coordinate, of course. As it turns out, the x and y coordinates of your torsion points are actually algebraic numbers themselves. So they are roots of polynomials over the ground field F. The key phrase here is that the x coordinates are specifically roots of so-called n-division polynomials. So there are polynomials attached to your elliptic curve which tell you the x coordinates of your n torsion points. Okay. And so if this is the case, then suddenly there's an algebraic number theory of torsion points on elliptic curves that you can study. So what kind of extensions do these torsion points generate? What kind of properties do these extensions have? And so on and so forth. And one way to understand these extensions, or these torsion points in general, and their rationality is the phrase, is by studying the division fields and Galois representations of elliptic curves. Okay. So the division field has a pretty straightforward definition. If I have an elliptic curve E over F, and I take a positive integer n, I can let f of E of n denote the n division field of my elliptic curve, and I get this n division field by adjoining to the ground field F all the x and y coordinates of my n torsion points. Okay. So I noted before that the coordinates of torsion points themselves are algebraic numbers. So at least if I attach the x and y coordinates of one point at a time, that's still going to keep a number field, right? It's still a finite degree extension of your ground field F. But in fact, I noted before that there are exactly n squared points of order dividing n. In particular, there are finitely many n torsion points. So I'm adjoining a finite amount of coordinates. And so therefore, this division field is also a number field with F. Okay. To make this a little more concrete, I want to consider an example. So this example elliptic curve is y squared equals x cubed minus 2x. And I want to compute the 2 and 3 division fields for this elliptic curve. So as it turns out, and this is not so hard to show if you know a little bit about basic elliptic curve theory, the two torsion subgroup for this curve consists of 4 points, as we expect. There's the identity element 0. But you also have the points 0, 0, and plus or minus the square root of 2, 0. Okay. And you might think about how this connected to the equation for my elliptic curve. The two torsion actually is very nicely characterized by the roots of the polynomial on the right-hand side of this equation. But then the two division field is not so bad, because if these are the only points I have that are order dividing 2, then I just adjoin all the x and y coordinates. The only non-trivial, non-rational coordinates are the plus or minus root 2. And so my two division field is just this quadratic extension, q adjoin root 2. Okay. Relatively simple two division field. Now if you go to the three division field, it suddenly gets a little more complicated. If you, I guess, put in the work, you can show that its three torsion subgroup consists of these 9 points. So there's the identity point of order 1, and then the remaining order 3 points are of this form where I have alpha in the x coordinate, and then this plus or minus square root expression involving alpha plugged into this polynomial, where alpha is plus or minus square root of 2 plus or minus 4 over root 3. In the grand scheme of things, it's not so complicated because it's square roots of square roots, which is nice, but it's also kind of nested calculations. You can calculate this with the 3-division polynomial, for example, right? Get your x coordinates and then plug, just solve for y in your expression when you plug in alpha for x. As it turns out, this, if you look at the 3-division field attached to your elliptic curve, where you adjoin all these coordinates, this ends up being a Galois extension of q, meaning it's normal. And in fact, it's going to have degree 16 over q. And you can show with some extra work that you have these two elements inside your 3-division field. You have the imaginary number I and a real fourth root of 3, for example, in this field. And because of this, you can combine them in an intelligent fashion. You can guess how you do this, to get a primitive cube root of unity living inside your 3-division field. Right? This is just essentially gotten from I times the square of this number, and then you just divide by 2 and subtract 1/2. But you can find that a primitive cube root lives inside your 3-division field for this example. And a primitive cube root here just has multiplicative order exactly 3 in the complex numbers. Okay. I want to show you a picture of the, I guess, arithmetic of this 3-division field. I don't want to focus too much on the details on this slide, but I just want to show you that, the division fields can get more and more complicated, and they're expected generally to be pretty complicated, but in a certain predictable way. But there's this nice sort of symmetry, and you get sort of pretty Galois theoretic picture, of subfields of this extension, and you can imagine that there's a corresponding picture on the right-hand side of the subgroups of your Galois group with the arrows reversed. But you can explicitly describe all these subfields of this 3-division field, and you get some interesting elements showing up. Q adjoin zeta 3 is the one I'm bringing your attention to because that'll be important later. But you can map everything out for this 3-division field. And then the 2-division field, which is this quadratic extension, which is much more simpler than this one, which is surprising. Okay. So I'm bringing this division field up, and we're interested in studying torsion points. And this division field is sort of capturing all the torsion points at once. But I want to leverage this to understand torsion points individually. And the way I'll do this is by writing things out explicitly as Galois actions. So as it turns out, any elliptic curve is going to have all the end division fields of any elliptic curve will be Galois over the ground field. And this is intuitively because it's going to contain the splitting field for these end division polynomials, along with these quadratic extensions from essentially solving for the y coordinates of these end torsion points. Okay. But these extensions are always Galois. Then I get an attached Galois group for this. I'm going to call this G sub n for the end division fields Galois group of my elliptic curve. And you can have this group act on the full end torsion subgroup. So first of all the coordinates of end torsion points live in this end division field f of v of n. So it makes sense to apply automorphisms of this group to coordinates of points in here. And in fact, I do the most natural thing, which is take my point x comma y, my end torsion point. I have sigma and automorphism act on it by acting on the coordinates. So something important to note in checking that this is a group action is that this action is going to take the n torsion subgroup to itself. And in fact, it will, by this simple fact, that if you have n times sigma of p, the n and sigma can swap. This is equal to sigma of n times p. And then if n times p is 0, so is this expression. And the reason this works is because this multiplication by n map is f rational. So if you apply sigma to n times p, this expression of quotients of polynomials over f in terms of the coordinates, you can pull the sigma over all the coefficients and end up with n times sigma of p on this side. But it is a group action on E of n, and you can check the other two properties for a group action. And of course, every group action gets an associated group action homomorphism. This one is called the mod n Galois representation of my elliptic curve, and it's often written as rho sub e comma n. It's a way to realize your elements of your group as automorphisms of the set E of n. Okay. And as it turns out, this is a faithful group action, meaning that if a group element acts trivially on all the elements of E of n, then that group automorphism had to be trivial as well. Right? And this is not something so hard to check, but it might be good to verify it for yourself. Yeah?
Quick question.
Yeah.
Curious. What is the Galois group?
Yeah, so I actually spelled out a little bit on the slides. I said at least from Q to this extension here, the alpha I, this is going to be the dihedral group of order 8, and then this is a quadratic extension. So in that case, it might be worth thinking about what the Galois group of the entire thing has to be. Yeah. Okay. Any other questions? Okay. So I get this associated group action homomorphism from my group action of the n division field Galois group on the n torsion subgroup. Now, normally you just have a way to represent your group elements as bijections on this set you're acting on, but there's an extra structure on this n torsion subgroup that lets you get a little more. So first of all, being an abelian subgroup of an abelian group, E of n is a Z module, but in fact everything has order dividing n, so it's a Z mod n Z module. And in fact, sort of by our argument a second ago, this Galois action I've written up here respects this structure, which is to say that if sigma of m times, well, it's to say that sigma of m times p is m times sigma of p for the same reasoning this line held. So in fact, this is now an action that respects the Z mod n Z module structure on my n torsion subgroup. And by the way, this is just like saying, if you don't know, you have like a vector space over Z mod n Z, but Z mod n Z isn't a field per se necessarily, so I'll just say it's a module instead. But in fact, you know a little bit more about your n torsion subgroup. It's not only a Z mod n Z module, it is a free rank 2 Z mod n Z module, meaning it's two-dimensional over Z mod n Z. This means a lot for our representation. So first of all, I represented my group elements as bijections on E of n. With the Z mod n Z structure, I can represent my group elements as linear maps on this module. But in fact, this is two-dimensional, so I can represent my linear maps not only as isomorphisms, but they are, if I pick a basis, 2x2 matrices. So now my representation, once I fix a basis for E of n, becomes a map from Gn into GL2 of Z mod nz, which is the general linear group of 2x2 invertible matrices over Z mod nz. This is just saying that this is a module over Z mod nz, and this is a two-dimensional object being acted on, so my linear maps are matrices. Okay? And in fact, they're invertible because they are isomorphisms. And if you change the basis for your n torsion group, it's going to conjugate the images of the matrices here, okay? But in a predictable way. So the point is, you can make this Galois action very explicit by picking a basis for your n torsion subgroup. And everything's explicit as matrices. To be more concrete, if you pick a basis p comma q, then you can have an automorphism in your Galois group look like the matrix ABCD if it sends p to AP plus CQ, and it sends Q to BP plus DQ. So this first column is recording where it sends P, and the second column records where it sends Q. But the point is you can actually write a matrix down for your automorphisms to represent it under this group action. Okay. And this actually tells you a lot about torsion points. So for example, if you have an elliptic curve, E over F, and a point P of order n, if you want to know whether or not its coordinates live in F, you can measure this by what your representation looks like. So your point P is F rational if and only if, with respect to the basis PQ, where you've chosen Q appropriately, your mono representation lives in matrices of the form 1 star 0 star. And the reason this is true is because, in general, if an automorphism sigma looks like 1 star 0 star, it's taking P to 1P plus 0Q. And if this is the case, the sigma fixes the x and y coordinates of P. So by Galois theory, the x and y coordinates, if they're fixed by all the automorphisms in your group, they're in the ground field F. So this tells you exactly whether or not your point was F rational. And in general, if you just want to know about the existence of an F rational point, sort of less coordinates in your information, you know that E has an F rational point of order n if and only if its mod n Galois representation image is contained in this type of subgroup of matrices up to conjugate C. Okay. So already the shape of your matrices in your modern representation will give you information about your torsion points and their rationality. Okay. And there's a lot of other structures that you can try to understand and what they imply on torsion. So for example, if this were upper triangular instead of 1 star 0 star, you would be able to deduce that there is a Galois stable subgroup, is the phrase they use. So some cyclic subgroup of order n, which is stable under this action of Galois. There's a bunch of other shapes that also tell you about different things as well. Okay. So do we have any questions so far? This marks the point of the talk where I'm going to switch into the research project. Okay. Oh, I didn't see it. Oh, yes.
Do we know when the map from GN to GL2
The map from GN into GL2? Yeah, so this is yeah, it should always be the case if you're looking at what's called almost always. You're looking at a non-Sam elliptic curve. In this case, there's some type of very powerful theorem which says that for large enough primes, you're always surjective. At non-CM. So the idea is if there's a subtlety here. If you change the target group, even if it is a CM elliptic curve, you can have it be surjective on the right type of group. But in fact, yeah, this action is going to be as large as possible in the sense that, or rather, you're going to have maximally algebraically independent, I guess, n torsion points, for example, when n is prime, most of the time for these elliptic curves. Okay. Yeah. I mean, yeah, okay. Any more questions? Something you can do for yourself as well is we had these two examples of division fields. You can check the, that's actually forward. I should be going backwards. Okay. You can check the degree of these extensions. And you can check the size of GL2 of Z mod 2Z and 3Z. And you can check whether or not these degrees are as large as possible. In that case, you can also determine in this example that this 3-division field should be surjective onto GL2 of Z mod 3Z, but of course not onto GL2 of Z mod 2Z. Okay. Any more questions, though, about division fields? Yeah.
Is the fact that En is free of rank 2 particular to this elliptic curve?
No, it's for all elliptic curves. Well, so I said at the beginning of the talk, let's assume our ground fields F are number fields. And if I didn't, I'll do that now. Our ground fields are number fields, unless otherwise stated. In this case, our n torsion subgroup is always rank 2. But in fact, funny things can happen when you change your field. And so, for example, if I just focus on the prime case, your p torsion group might even have rank 1 or rank 0, depending on the field you look at. But over number fields, this never happens. Yeah. That's a good question. Any more questions? Okay. So if not, I want to talk next about a project I had with a student from Ohio State. His name is Sam Allen. And this is a project I organized as an undergrad research project through a program called Cycle at OSU. This project was on understanding the so-called cyclotomic division fields of elliptic curves. Okay. And so to start this discussion of the project off, I wanted to tell you what, or review cyclotomy of C. So cyclotomic elements are also called roots of unity. So recall that a root of unity is an element of C, say non-zero, with finite multiplicative order. So it's a zeta such that there exists a positive n for which zeta to the n is 1. Okay. And if you want to emphasize that its order is exactly n, you can say that this is a primitive nth root of unity. And I'll write it as zeta sub n. So already an analogy to elliptic curves. We have elliptic curves and torsion points, and now we have C star and roots of unity. And there's a lot of connections, a lot of deep connections between elliptic curves and roots of unity or cyclotomic elements. One connection is the fact that you always have a primitive nth root of unity in your n division field for your elliptic curve. So zeta n is always in f of v of n for any elliptic curve you look at. Okay. So in a way, if you're trying to understand the n division field, which tells you the Galois action how your torsion points look in terms of rationality, you have a lower bound on the arithmetic complexity of these fields given by the cyclotomic fields, or the n cyclotomic field specifically. Okay. Well, if you always know that these roots of unity live in your n division field, you can ask questions like, how much more do you have from this extension to that one? Another question you can ask also is, when are these two fields equal? AKA, when you have no more arithmetic information in your n division field. If the n cyclotomic field is equal to the n division field of my elliptic curve, I'm going to say this division field is a cyclotomic division field, fittingly, or a small division field. Okay. So we had this example for computing 2 and 3 division fields of elliptic curves, and we actually kind of already noted a little bit about this. We know that the primitive cubital unity, zeta 3, lives in here, and I gave you a representation for that. And then I noted, as you can check, that the degree of this extension is 16, the 3 division field. Well, we also wrote out zeta 3, but its degree should be 2 by the Euler-Phi function as well, if you're familiar with that. Well, the degree of this subfield is 2, and this is 16, so of course they're not equal. And so therefore my 3 division field is not small. Okay. It's not small means that there's more arithmetic in the torsion points than is just captured by the roots of unity. Okay, well, I've curated this example for you all, so maybe it's natural to think about what happens with other elliptic curves beyond this example, right? And so something I had my student do was just make some preliminary magma code. It's not meant to be read, by the way. I made it small so you don't really analyze it. This is a mathematician's code. It's not a programmer's code. We did our best. But I had him do some preliminary calculations, and just to check the frequency of small division fields and maybe the levels of the division fields which appear, the n's. We did this over various number fields. Data was pulled from the LMFDB. We had some examples. We did, this is just 3 examples color-coded, but we did several dozen. And something that we spotted was that small division fields are uncommon over number fields. And in fact, small division fields only really happen for small n. So what I mean is that in our calculations, I think we were getting n at most 7. So it seemed like an absolute bound on these levels of division fields. So that led us to conjecture a few things and try to prove other things. But I should also say that if you restrict your attention to Q, so the simplest number field, there's actually a known result in this direction. So rather fittingly in 2 ways, we have a result of Enrique Gonzalez-Jimenez and Alvaro Lozano-Robledo. So this is a result for small division fields over Q and abelian division fields. But also fittingly, I want to bring to your attention is this was 2016, it was published. So it was 10 years ago in the year of the first CTNT. So they show that if you have any elliptic curve over Q, if you have a small n division field, then n is no more than 5. And more generally, if you have an abelian division field, then n is no more than 8. Okay. That's pretty interesting because, of course, there's a lot of elliptic curves you can come up with non-isomorphic over Q with all these varying division fields that can appear. And yet there's this sort of absolute bound on both these levels, the small division field case and abelian division field case. I don't think they called it small division fields in the past, but they had results for this type of field. And so I want to point out that they proved this with lots of different techniques and ideas, but sort of two very prominent ideas were using careful group theoretic considerations on your mod n Galois representations as matrices. And they also did explicit calculations with these so-called modular curves. So again, this talk is meant to be geared towards the students of CTNT. Modular curves are sort of an advanced topic, and there will be talks covering modular curves in this conference, which you should attend. But the short of it is that like modular curves are this sort of moduli space for elliptic curves with torsion structure, where if you have a modular curve, say defined over Q, and you take a rational non-cuspidal point on this modular curve, somehow that's telling you about the existence of an elliptic curve over Q with a specific torsion structure. Maybe it's a torsion point defined over Q or a rational cyclic subgroup of your elliptic curve. But the point is that you can study modular curves and their rational points to deduce, for example, there exists no elliptic curve over Q with that type of torsion structure. You can do this by showing that this modular curve has no rational non-cuspidal points. But again, it's an advanced topic. People will talk about it in their talks, though. You should attend them. But the idea here is, over Q at least, we know a lot more about Galois representations of elliptic curves and, because of, modular curves. So over Q, they can use known results. They can also prove more results over Q to prove this type of result on small division fields and abelian division fields. Okay. So if you want to pass from Q to a larger number field, you lose a lot of known results that were known over Q, because in general it's harder to study Galois representations, for example, in modular curves over arbitrary number fields. Okay. Despite this, me and my student were able to prove the following theorem describing the small division fields and abelian division fields over general number fields. So the results is as follows. If you start off with a number field f and an elliptic curve over f and a prime p, if you have a small p division field, then the prime p is uniformly bounded in terms of f. And also more generally, if you have an abelian p division field, then p is uniformly bounded in terms of f. The caveat is this abelian situation here needs some 2 extra hypotheses to be proven, at least the way we proved it. I'll just state the hypotheses for completeness. You need to assume for our proof that this is going to seem like a big assumption, but it's common in math. The generalized Riemann hypothesis has to be assumed true. Again, you can control F, generalized Riemann hypothesis, or just search it on Google and you'll see a lot of papers assume this. But you also want to assume, a little more technically, that F does not contain the Hilbert class field of an imaginary quadratic number field. And the idea is if you combine these two assumptions, you can bound uniformly the rational prime degrees of isogenies over your number field F, which helps us eliminate the so-called Borel case in this abelian case for our theorem. Anyway, we're going to focus on the small division field result for this talk. Yeah? That's a good question. So the result that we're trying to use here for the abelian case is bounded in several invariants of F. It's not a strong uniform bound necessarily. Ask a question. But I'm sorry? Yeah, there's no. Yeah, that's fine. Allowed BCM. Yeah. Yes. Yeah, I guess if you're working in the abelian case and you're working with this number field which has no rationally defined CM, you can work with CM elliptic curves, but their endomorphisms are not defined over F. That's a good question. Okay. Any more questions? Right. So regarding these bounds, I said uniform bound. Uniform bound means that the bound depends on the field F. So you can vary your elliptic curves over your ground field F, but no matter what, if you have a, for example, small p division field, you get a bound on p in terms of your field and not your curve, right? So here's a little bit more information on the bounds. If you have a small p division field, then if your prime is bigger than 12 times a degree plus 1, you are forced to have an order p point over an extension of f of degree bounded in terms of the degree of f. Okay. The thing is, you can also bound the orders of prime orders of torsion points over a number field by famous results due to like Lock-Morel or Perrant in terms of the degree of your extension of f over q. And so the idea is, well, the conclusion is, if you have a small p division field over a number field, then you can actually bound p in terms of the degree of your extension. Okay. This is called a strong uniform bound because not only does it not depend on any other, well, it depends on the degree of your number field, but that's it. So this bound that we have works for any elliptic curve over any number field of a bounded degree. Okay.
You're saying the first part of the theorem only does depend on f to its degree of q?
Yes. Yeah, exactly. And then for the abelian case, if your prime is bigger than 12 times the degree plus 1, the information is a little different. Your mod p image is contained in a Cartan subgroup of GL2 of Z mod PZ. And with our technical assumptions, this is sufficient actually to get uniform bounds on p. But in this result, your bounds are depending on other invariants of your number field. So it's a little harder to narrow down. Okay. So I want to show you the techniques we have for this paper and hopefully show you or convince you a little bit that it is doable by a student. Do you have any questions so far? Yeah. Yeah, well, I'm going to show you the technique we had, and the technique requires us to work with the prime, and I'll explain why it doesn't work if you don't. Yeah, that's a good question. Yeah.
For the first part, the inequality strict, so can you always find the elliptic curve over whatever the bound?
I'm sorry, what was the first part? If the what strict?
The inequality, whether it's a strict
Oh.
inequality or can you prove it better?
Oh, yeah, I mean, like the idea is we show that if you have a small p division field, no, yeah, so I guess you can do better. Yeah, you can do better potentially. But the point is that if you assume p is too big here, then you're forced to have a certain image of Galois, which then puts us in the situation to apply these other uniform bounds on prime orders of torsion points. That's a good question. Yeah, these aren't necessarily sharp. And like I said, the calculations we did showed that p at most 7, or if you have a small p division field, then p should be at most 7. So with other techniques, it might be even better, but who knows? Good question. Any more questions? Okay. All right. So I want to show you some of the ideas we had for our proof. I want to focus on the cyclotomic division field case and forget about the abelian case for now. So like I said before, we lose sort of a wealth of results for Galois representations, elliptic curves, and specifically modular curves, or generally modular curves, when you pass from Q to a larger field. So we had to do a different type of analysis. And so we utilized this relatively simple fact. I don't think this was used in the paper over Q, but if you have a small n division field, this is equivalent to having an intersection be trivial with SL2 of Z mod NZ. So here, these are your matrices in your mod and Galois representation image. This is the matrices of determinant 1 over Z mod NZ. Okay. So this actually puts pretty strong constraints on what your mod and image of Galois can be. Okay. So for example, this says that your subgroup is isomorphic to its image under the determinant map. Okay. Okay. And that works for all n. So then the question becomes, why are we working for prime p? And the idea is that we had a technique here where we analyze the image of Galois above and below. And so this works for prime levels p. So there's a classification of subgroups of GL2 of Z mod PZ, which holds when p is prime. This is the algebraic component. And then there's an analysis of the image of inertia on the p torsion group of an elliptic curve due to work of Serre. And this is the arithmetic. Okay. And so the idea is That's kind of a funny description, I guess. We have like sort of a sandwich. We have two buns, and then we have this ingredient, which is like a thick patty. And this is intersection with SL2 is trivial. This is your small division field. And then we squeeze this patty with the buns, the algebra and the arithmetic, and this is sufficient to get a uniform bound on your prime level P. Okay? And this is why I have to work mod P, because this results for P and this results for P, not necessarily for composite N. Okay. Okay. So we'll start with the upper bound on the shape. This is the algebra. This is a classification of subgroups of GL2 of Z mod PZ. This is due to Sayre, and it was in his famous paper on the open image theorem, but this is essentially due to Dixon. So I might just call this a Sayre-Dixon classification of subgroups of GL2 of Z mod PZ. But the idea is, just by algebra, if you have any subgroup of GL2 of Z mod PZ, then this subgroup has one of the following four shapes. It either contains SL2 of Z mod PZ, or as well. So this is all up to conjugacy, so I don't have to keep saying up to conjugacy. So this actually doesn't matter up to conjugacy, the first property. Either G contains SL2, or G is upper triangular, or G is contained in the normalizer of a so-called split or non-split Cartan subgroup, or if you mod out by the scalars inside of it, this quotient is isomorphic to A4, S4, or A5. These are the alternating and symmetric groups of size 4 and 5. Okay. So 5 possible shapes, really. I just grouped the Cartan cases together. This is true for any subgroup of GL2 of Z mod PZ, and we know that our mod N image of Galois, where N is P, is a subgroup of GL2 of Z mod PZ, so it admits one of these four shapes, right? But furthermore, in our project, we're assuming this extra piece of information where we intersect SL2 trivially. And so because of this, this actually simplifies even further. So first of all, you can't contain SL2 in this setup, right, if you intersect it trivially. Your quotient can't be one of these groups. It's not abelian. And in fact, if you're upper triangular, you're forced to be diagonalizable. Bless you. And if you're in the Cartan situation, here's just sort of 2 or 3 cases to consider. If you're not in the Cartan subgroup itself, but you're in the normalizer properly, then in fact, your subgroup is generated by scalars along with some non-Cartan element in G. And all this is meant to just show you that your mod P image of Galois simplifies considerably. And this is for free. This is for any subgroup of GL2 of Z mod PZ. But under our assumptions, our subgroup becomes a lot smaller. Right. Okay, so that's the, I'd say, the upper bun to the sandwich. This is the algebraic component. And so there's a lower bun, which is the arithmetic component, but I guess I'll just show this up here first. I don't want to go through all the subgroups, but the point is that we have these Cartan groups appearing, and they're normalizers, and they're very explicit and concrete. You can actually write something down, okay? But don't get caught up in the details of how to define these things, but they exist and you can write them down, meaning that our classification is very explicit here. Okay. Now, there's an arithmetic component to the project, and by this I mean that there is this work of Sayre on the action of inertia on your p-torsion group that we use. So there's a way to phrase his results, essentially in purely group theoretic terms. And so this is one version of it. The theorem we have in our paper is longer, which means there's more cases to consider. But the idea is, depending on the action of the inertia group, you're getting guaranteed subgroups of your mod P image of Galois. So I'll just say some things here. So E over F be an elliptic curve and P of prime. We're going to let this fancy P be a prime and F over P. I'm going to let E denote the ramification index of this fancy prime P over P. And under some assumptions to just simplify the presentation of this result on this slide, you get one of 2 cases happening. You either get that you have all ETH powers of matrices of the form star 001 showing up in your mod P image of Galois, or your mod P image of Galois is going to contain the ETH power of the non-split Cartan group, which again, I don't want to linger on the definition too much here, but it's something you can actually write down concretely. Okay. So we're getting one of two guaranteed subgroups for our mod P image of Galois, which is telling us more about the structure of our mod P image, right? Well, in our setup, the way we use this is as follows. So the non-split Cartan is like roughly essentially size P squared, and then your mod P image of Galois, because it embeds into Z mod PZ star, is roughly size P. The point is you can use a size argument to show that this forces P to be less than E plus 1, because E showing up as the exponent of the non-split carton. If you're in the first situation, which is for good ordinary or bad multiplicative reduction, then in fact you have to do a little more case-by-case analysis with the shapes from the algebra classification. So depending on whether or not you're upper triangular or the normalized with a split carton group or non-split carton group, you have to analyze what you know about your subgroup, or which cases can or cannot happen. And for the cases that can happen, what can you say about P in terms of E? And the reason this is sufficient for a type of bounds is because if you bound P in terms of this ramification index, you know the ramification index is bounded by the degree of the total extension, F over Q. And so you get your uniform bound P in terms of F over Q. So omitting some details here, this is how E shows up to bound P in terms of the degree. E shows up, and thus the degree, because we have this action of inertia in the arithmetic coming from Serre's work. Okay. And this is just a simplification of the actual results in the paper, because it's kind of a lot to state otherwise. So there's some cases we have to deal with that I didn't mention here in the small division field case, but also in the Beeling case, we have a lot more work to do. Okay. Okay, so this is just summarizing how we tackled this problem. The idea was we had this sort of above and below upper bounds on the structure of a mod P image, and then this final ingredient was the intersection of SL2 was trivial, and this was enough to uniformly bound P in terms of the degree of our number field in the small division field setup. Okay. So as you can imagine, with all these matrices appearing, a good chunk of this paper involved elementary group theory calculations, and with some steps for Galois theory conceptually. So that's what I had him work on, the student on this paper, Sam. He did a significant amount of the group theory calculations with matrices to reduce the cases we had to consider, and then we could throw these theoretical results to get the uniform bound that we wanted. Okay. We have a preprint for this. Our results are already proven. You can find an archive pretty easily. Just typing in cyclotomic division field is sufficient. Okay. So the talk's almost done here. I think I'm over time. But let me just mention this quickly. This project sort of sets up a framework for potential future projects, in that we have these buns, the upper and lower bounds, the algebra and the arithmetic, the classification of subgroups of GL2 mod P, and this action of inertia a la work of Serre. And then the middle ingredient can change into something else that interests you. So instead of doing small division fields, you can replace it with nilpotent division fields, which has been studied over Q, solvable division fields, whichever adjective you like for groups or for division fields with the curves, you can swap out this middle piece, this patty, with this other assumption and see if you can get uniform bounds on P. Okay, because the result we state from Serre is already stated in our paper. It's essentially purely in terms of group theory. You can actually probably prove something interesting just using these above and below bound techniques. Okay, so if you have a favorite adjective, let me know after the talk. I'm always looking for more papers. Okay, and then I'll just show this slide here. So there's two students who did the reading portion of this project presented what they learned at this thing called the Cycle Fair at Ohio State. So in the middle is David Cruzel, who was here for the reading portion of the project, but he graduated that spring and wanted to focus on his grad school starting in the fall, so he opted not to do the research portion. But Sam Allen's to the left, and he actually worked in the research portion as well, and we did a lot of work over the summer on this paper. So I'm very proud of them for the stuff they learned, and then Sam for doing all this research work. But that is all. Thank you for listening.